Welcome to video lecturing on BSc first semester mathematics. This is session 27. In this session we are going to study on the verification of Cayley-Hamilton theorem and determination of inverse of a matrix A. In the previous session we have studied the orthogonal and unitary matrices and their properties, and the learning objectives of this session are finding the inverse of a matrix and verifying the Cayley-Hamilton theorem. After the completion of this session, students are able to understand the way how to find the inverse of a matrix using Cayley-Hamilton theorem and also to verify the Cayley-Hamilton theorem. Let us take an example in this. Verify Cayley-Hamilton theorem for the matrix A is equals to first row 3, 4 and second row is 3, 2. Let us take this matrix A as it is, and to verify the Cayley-Hamilton theorem, first you have to find the characteristic equation. That is, characteristic equation is determinant of A minus lambda I is equals to 0. First let us find A minus lambda I. It is equals to matrix A minus lambda into matrix I, unit matrix. So it is 3 minus lambda, then 4, then 3 minus lambda into 0 is 0. So it is 3 and it is 2 minus lambda. Here for finding this A minus lambda I, the shortcut is you have to take minus lambda to the diagonal elements. That is, we have 3, 2, no? Take minus lambda and for 3 and it is also for 2. That is 3 minus lambda and the remaining elements you keep as it is, 4 as it is, 3 as it is and 2 minus lambda. You will get like this here. And determinant of A minus lambda is equal to determinant of 3 minus lambda, 4, 3, 2 minus lambda is equals to 0. And next step is we can simplify this determinant here. It is 3 minus 2, 3 minus lambda into 2 minus lambda minus 12. So next is 3 minus lambda into 2 minus lambda minus 3 into 4 is 12. Open this bracket. You will get lambda square minus 5 lambda minus 6 is equals to 0, which is the characteristic equation of matrix A. To verify Cayley-Hamilton theorem, what you have to prove is here, you have to prove that matrix A satisfies this equation. So that is, we have to replace lambda by A, that is A square minus 5A minus 6I you have to take here, because it is a matrix, no? All elements should be in the form of matrix only. Take I, 6I, it is equals to 0. This you have to verify. That is, A square minus 5A minus 6I should be null matrix. This you have to verify. For this, let us consider A square. A square is equals to A into A. That is, you know how to find the product of these two matrices A into A. It is first row by first column. That is 3 into, after simplification you will get here 3 into 3. This is 9 plus 4 into 3, it is 12. First element. Then next element is here first row into second column. Corresponding elements you have to multiply. 3 into 4, 12 plus 4 into 2, 8. Similarly, then second row, with second row you have to use the same, you have to find multiplication. Second row into first column. 3 into 3, 9 plus 2 into 3, 6. Again second row by second column. 3 into 4, 12 plus 2 into 2, 4. Like this we can find the product of two matrices. You will get, after simplification you will get 21, 20, 15, 16. Now consider A square minus 5A minus 6I is equals to. Substitute all the values. A square is 21, 20, 15, 16 minus 5A is 3, 4, 3, 2 and minus 6I. I is the unit matrix 1, 0, 0, 1. Open this bracket and simplify. You will get, this one is, open this bracket, you will get here 21, 20, 15, 16 minus 5 into 3 it is 15, then 5 into 4, 20, then 15, 5 into 2, 10 minus 6, 0, 0, 6. Like this you will get. Add the corresponding elements. 21 minus 15 minus 6. 21 minus it is also 21. This is equals to 0. Similarly, 20 minus 20, it is also equals to 0. And next is 15 minus 15, it is also equals to 0. 16 minus 10, this is next element is 16 minus 10 minus 6. You have to add the corresponding elements, you will get it is also equals to 0. What we got? We got this is a null matrix. This implies Cayley-Hamilton theorem is verified. What we got? The every square matrix satisfies its characteristic equation. When you replace lambda by A, then you should get a null matrix. This is the verification of a Cayley-Hamilton theorem. To find A inverse, what you have to do is you have to multiplying equation 1 by A inverse. That is, you have to multiply the characteristic equation by A inverse. We know characteristic equation is A square minus 5A minus 6I. No? You have to multiply each element with A inverse. A inverse into A square minus 5A inverse into A minus 6A inverse into I is equals to O. We know A inverse into A square is A minus 5A inverse into A is I, that is 5I minus 6A inverse into I is A inverse. 6A inverse is equals to O. We want A inverse now. Take 6A inverse in RHS, it will be plus. So this implies 6A inverse is equals to A minus 5I. You have to substitute the values of A and I. A is 3432 minus 5, I is 1001. Now again you have to simplify this. You know how to simplify this. This is 3432 minus 5 into 1 is 5005. Corresponding elements you have to subtract. 5 minus, this is 3 minus 5. Next 4 minus 0 is 4. 3 minus 0 is 3. Then 2 minus 5. Here you will get like this. After simplification you will get minus 2, 4, 3, minus 3. This implies A inverse equals to take 6 in RHS. It becomes 1 divided by 6 into minus 2, 4, 3, minus 3. This is A inverse. If you want, you can verify this whether it is correct or not. We know how to find the inverse of this matrix. That is, we know A inverse. We know A inverse. We have two methods to find this. A inverse is equals to, one method is adjoint of A divided by determinant of A. This method also we use. Otherwise, we can verify here A into A inverse should be I. Multiply A with A inverse, you should get I. This is also one of the method to verify whether you have done correctly or wrong. Let us take one more example. Verify Cayley-Hamilton theorem for this 3 by 3 matrix. Let us take, the method is same. Let us take matrix A, the given matrix. Next you have to find A minus lambda I, that is A minus lambda I. I told you how to get this A minus lambda I, that is for diagonal elements you have to take, for these diagonal elements you just take minus lambda and write the remaining terms as it is. That is 1 minus lambda 0 2, 0 2 minus lambda 1, 2 0 3 minus lambda, and find the determinant of this one. You know how to expand 3 by 3 determinant. You will get 1 minus lambda into 2 minus lambda into 3 minus lambda plus second element into minus 2, and because here second element is 0, 0 into anything is 0, and third element is 2 into minus 2 into bracket 2 minus lambda. After simplification of these brackets, you will get lambda cube minus 6 lambda square plus 7 lambda plus 2 is equals to 0, which is the characteristic equation of matrix A. To show that A satisfies this equation, we need to prove A cube minus 6A square plus 7A plus 2I is equals to O. That is, you have to consider, first you have to find A square, that is A into A. I hope all of you know how to find this matrix multiplication. The last slide only I have told you, first row with first column, then first row with second column, first row with third column, like this. Second row first column, second row second column, second row third column, and lastly third row first column, third row second column, and third row third column. You will get this product. That is, it is equals to, you will get 508245803. We want A cube. A cube is equals to, we know, A square into A. That is A square into Once again I will tell you how to find this multiplication. This is first row with the first column you find. That is 5 into 1 is 5, 0 into 0 is 0, then 8 into 2 is 16. First row into first column is over. Next is first row into second column it is. Corresponding elements you have to multiply. 5 into 0 is 0, then 0 into 2 is 0. This next is 8 into 0 is 0. You will get this element. Similarly, first row into third column. Corresponding elements you have to multiply. 5 into 2 is 10. This element you will get. 0 into 1 is 0. 8 into 3 is 24. Next, second row into first column. 2 into 1 is 2. 4 into 0 is 0. 5 into 2 is 10. You will get this one. Next is second row into second column. That is 2 into 0 is 0. 4 into 2 is 8. 5 into 0 is 0. You will get this element. Lastly, and the next one is second row into third column. Corresponding elements 2 into 2 is 4. And 4 into 1 is 4. 5 into 3 is 15. Lastly, third row with first column. 8 into 1 is 8. 0 into 0 is 0. 13 into 2 is 26. This one. Third row into second column. Corresponding elements 8 into 0 is 0. 0 into 2 is 0. 13 into 0 is 0. And lastly with third column you have to multiply. That is 8 into 2 is 16. Plus 0 into 1 is 0. 13 into 3 is 39. After simplification you will get this 21 0 34. 12 8 23. 34 0 55. This is a cube. Next, consider a cube minus 6a square plus 7a plus 2i. We know all the values. Let us substitute all the values and simplify. This one is very common. You can simplify this one. First you have to write a cube as it is. Then 6 into a square plus 7 into a plus 2i. We know all the values. Let us simplify this one. And after simplification you have to add the corresponding elements. You will get 0 0 0 0 0 0 and it is a null matrix. This implies a cube minus 6a square plus 7a plus 2i is equals to 0, which satisfies characteristic equation. Hence we can say that Cayley-Hamilton theorem is verified. I have given some multiple choice questions. You solve these examples yourself and I have given answer also. But you have to solve this one, then only you will get the answer. First equation is the characteristic equation of this matrix. You know how to find the characteristic equation. Characteristic equation means here determinant of a minus lambda I is equals to 0. In this case you should get, you have to, that is 4 minus lambda 3 to 9 minus lambda. Simplify this, you will get this result. Next one is inverse of this matrix is. To find the inverse of the matrix, use any method, not only this Cayley-Hamilton theorem, you can use your own method also. And next one is inverse of this matrix, same question. And lastly, and fourth one is the characteristic equation of this matrix. Again it is also same. The characteristic equation of this matrix is, again here also you have to simplify this one. You will get this is to find the characteristic equation you have to take minus lambda to the column diagonal elements and remaining elements you have to keep as it is. Expand this, you will get one equation. This is about this today's session and these are the references I used for this session. Thank you very much for watching this video. Thank you.